My name's Phil Lynch, has been introduced there, and I'm with my colleague Dave, who's more on the sort of technology and process side of it. I was just on the presentation this morning. I'm conscious we've only got 20 minutes, so I've left some contact details at the end of the presentation, and I think Marian's going to share the slides that we're going to present this morning, and there's contact details in there. So as Mike mentioned, if there's any questions or anyone wants any more further information or just wants to chat about any opportunities or challenges they have, we're more than happy to do that. I'm going to give a quick brief introduction on Freudenberg and Aquabio. We're also going to look at the sort of the global sort of trends in the sort of processing water and water recycling and net zero, what have you. And there's both a sort of global trend, but there's also the local challenges it gives us as well. So I'll have a quick look at that. To try and sort of hone it in a little bit before Dave speaks about the actual technologies, I'll talk about the actual sort of target waste streams that we'll all sort of be used to. And then obviously we've got Dave will give a chat about the actual technologies itself, which you'll hopefully find quite interesting. And then there's, I think we've allowed some sort of 5 or 10 minutes at the end for any sort of specific questions that we can help with. So just quickly, Freudenberg. So myself and Dave, work for Aquabio. We were acquired by Freudenberg nearly 10 years ago now, actually. Freudenberg are a large family-owned German technology development and operational business. And you'll see with some of the numbers there, there's like a 10 billion turnover, pounds sterling per annum, employing nearly over 50,000 people globally. But what it does when they acquired us, what the real interest that they give us as a sort of as the mothership in theory, is the ability to feed down information on research and development. So it allows us to continue to develop our products that we actually bring to market. And because Aquabio are what we call an EPC contractor, so we take on full responsibility on customer sites from initial conception right through to the actual commissioning, building commissioning. There's a lot of process guarantees required. There's a lot of bank bonds put in place until the technology is up and running. So having a large company behind us gives us that sort of ability to be able to do that. As Aquabio, with three pillars, it's all really about saving energy, especially in today's world with the cost of energy, and a lot of the technologies that were developed are very much what we call low energy. So really looking at the cost of actually running them from an OPEX point of view. It's all about recovering resources, and water being one of the biggest resources to mankind, really. That's where our real focus has been for the last 25 years, is all about focusing on recycling water. And to keep every business going, it's all about reducing costs. So a lot of the technologies we've sort of topped and tailed and cleared over the last sort of 20 years. And it's all about, providing something that's robust, but at the same time is competitive in the marketplace. To keep things simple, we really operate two types of technologies. You've got aerobic membrane bioreactors, and that tends to look at, Dave will talk more about this, but it tends to look at the sort of CIP and the sort of low, high volume but low loading or low sort of contamination waste streams. And then you've got the anaerobic technology, which is an anaerobic membrane bioreactor, which basically looks at extracting organics from high load COD waste streams, where you can extract and actually convert the material into biogas, which convert into biomethane, which in theory is a renewable energy. And in both those applications, we can then add on the next step, which takes us into water reuse. It could get quite complex, a lot of this technology. So what our real USP is actually the ability to actually control it all by our own in-house sort of control and software packages, which is linked in with SCADAs. These type of plants, we've got 38 of the full-scale plants across the UK, and 5 of these membrane bioreactors are actually in the dairy industry. So we're well used to the sort of the waste streams and the challenges and the daily flows and CIP regimes and what have you from that industry sort of thing. So just quickly looking at the drivers, what we're noticing from a global perspective, and it's been picked up by a lot of people now looking at developing technology, is that there seems to be a new generation of consumers. So people are actually buying the end product, looking at how a product's actually manufactured, where it's manufactured, how much energy, what's their carbon footprint. And I think a lot of the work we do actually, and you probably pick up from the Scottish accent, is from the Scottish distillery market. And they've got a challenge. So if you imagine making a pint of milk and putting it in a carton, then putting it in a warehouse, and then trying to work out who's going to buy it in 10 years' time. Well, that's actually the problems that the distillery market have got, where they're actually, manufacturing a product now, but they're trying to work out who their market is going to be in 10 years. And they've realized that the market in 10 years are going to be a much more savvy audience and consumer that's going to be looking at what the carbon footprint is, how much energy they're taking, how clean it is, how they deal with their waste. And I think it's important now to actually to start looking at that the consumers are definitely driving the market and how products are actually made and manufactured. Cost, huge driver, always will be. I think there was mentioned earlier about just the changes over even the past 4 or 5 years in sort of world politics. Energy security is really important. If there's the option to take indigenous waste from any site and convert it back into energy, that has to be seen as a positive step forward. One from a corporate responsibility point of view, but also from a consumer point of view as well. And there's also legislation coming through as well, which we've probably heard of, called the IED, which is the Industrial Emissions Directive. So not only is consumers looking to move things forward from doing the right thing, really, there's now legislation coming through which will see sector specific over the next few years about emissions that are going back into the environment. And that's going to drive a lot of people into looking at what they can do. Can they recycle water? Can they recycle their waste stream into biogas or bioenergy? So what we're really seeing now is that doing nothing, if you look into the future, is probably not an option anymore, and it's going to be critical to the outline growth of the dairy sector. So that was the global look. If you look at the day-to-day issues that we all see on customer sites, there's limitations on water demand from network and aquifers. We're seeing there's huge issues on the east coast of England on water scarcity, where businesses are finding it difficult to grow because they can't get access to water. So the idea of actually recycling water could be quite interesting. We're seeing costs increase both for discharge consents and also for water coming in. So if there's an ability to actually recycle water, there's a huge cost-saving benefit there. And water and the management of wastewater is an ever-increasing and valuable resource because it's a cost. If you can manage that cost better, there's a solution in there. So the solution that we've got is actually to manage and valorize waste and byproducts, and in a lot of cases whey waste and things like that, on site to turn indigenous waste into local renewable energy or clean water. And how do we do that? Well, we've got the two types of technologies that Dave will come on and talk about. So you've got an anaerobic membrane bioreactor, which really is looking at liquids, and that turns waste into biogas or biomethane. And we've got an AMBR, which is an anaerobic membrane bioreactor with an RO added onto it. And what that's doing is that's taking water and actually cleaning it into potable water. So in theory, it can go back into product, which we're actually seeing in some sites now already, actually, which is quite interesting. I understand there's sometimes a bit of a psychological step about using recycle water back into product, but many industries now are actually doing that, but they're also taking it further. They're actually, let's say further, that they're also using it for CIP processes and general maintenance and cleaning. Just to sort of focus a little bit, so the waste streams that we would particularly target are, and I sort of touched on this earlier, so low to medium COD, so it tends to be high volume, low strength. That's typically you get from CIP regimes, and that can vary depending on what regimes are put in place at each factory or processing outlet. So having a technology and Dave will talk about this, that's quite flexible on how it receives material, what loads, what flows, it can fluctuate greatly actually. So having that flexibility in technology is really important. You then go into the more higher COD waste, which you've got a lot of sugars, which you can convert into biogas. So that's on-site indigenous energy, and that tends to come from whey and whey permate. And I'm sure we've all came across where you've got unused milk for whatever reason. There's that could be processed through this technology as well, actually. So I'll pass you on now to Dave, who'll sort of take you through a sort of technical walkthrough how the technology works. And again, there's some questions at the end if you need to, if there's any specific questions as well.
Thanks very much. Thanks very much, Phil. Morning, everybody. Right, our AMBR process. We take wastewater or feedstock, and this enters into our bioreactor. This bioreactor is a tank which is kept under anaerobic conditions, which is essentially in the absence of oxygen. Usually, but not always, some of the waste stream needs to be supplemented with some nutrients. This is to aid the biological process. Some of the streams are a little bit deficient in nitrogen, not necessarily phosphorus, but certainly some of the micronutrients. So there is occasionally an addition of a nutrient solution added to the waste stream to, like I say, to aid that biological process. Within the anaerobic bioreactor, as Phil's already alluded to, the organic matter is converted into biogas. So that biogas can then be utilized either to produce energy on site via boilers or steam generation, or on occasions that biogas could be refined or enriched and entered into the gas main national system and sold as an energy source to the public or other industries. Also occurring in the bioreactor, the COD is converted into a small amount of biomass. This is essentially the bacteria that are living on and producing the biogas, biomass rather than biogas. That biomass is constantly recirculated within the reactor. And as the level control system dictates, you'll see from the pulsating little blobs going around the flow diagram, a proportion of that biomass is recirculated through a series of UF or ultrafiltration membrane modules. It's that recirculation flow that creates sufficient pressure to drive the effluent across the membrane surface. The retained solids continue through the membranes and return back to the reactor to continue the biological process. The filtered effluent, which is now the light blue line, is now of sufficient quality that it could be discharged either to a watercourse, on occasions if the watercourse is large enough to accept that quality of water, or it could be passed on to tertiary treatment for further treatment. We also retain a small proportion of that permeate that we generate for back flushing of the membranes to help clean the membranes during the process. We also utilize a number of cleaning mechanisms to mitigate membrane fouling during this process. Next slide, please, Phil. So typical waste streams that are suited to the anaerobic process is you want to consider where you want to maximize the use of the biogas or produce a biogas from your waste stream, and that utilization of that energy is critical to your process, or is certainly seen as a revenue stream. You may also want to achieve higher COD removals to reduce the sewer discharge costs, and potentially produce, like I say, produce an effluent that you could discharge to a water body if that's applicable to your particular geographic location. Waste streams that are more, as Phil was alluding to, waste streams that are more applicable to the anaerobic process are high strength or organic streams. So with CODs, concentrations between 15 to 250 grams or 15,000 to 250,000 ppm of COD. Low to medium flow rates. Our anaerobic process can tolerate waste streams which have suspended solids up to 20,000 ppm or 2% dry solids. And when combined with our ANBR, RO and UV, the effluent produced can then be carried on and retreated to produce a water which is deemed potable or certainly utilized for reuse. Other benefits that we get from the ANBR process is that because we're using a membrane system, we're reducing or eliminating the suspended carryover from the process, and that mitigates the biomass washout. We're producing a very high quality suspended solids effluent. We've got the ability now, because we can decouple hydraulic and solids retention within the reactor. This allows the process to be run at relatively long slow gauges. This certainly helps with the degradation of some slowly degradable components within the effluent. Typically, we produce high COD reduction and biogas quality and yields, which are in excess of some of the other higher rate anaerobic processes, such as USAB and EGSB. Our process is also tolerant, more tolerant to suspended solids and fats, oil, and greases than a traditional granular sludge process. The low energy biomass separation system that we incorporate doesn't need flocculants or coagulants to aid that separation process. And typically the energy that we will consume during the membrane process will be between 1.5 to 2.5 kilowatt hours per meter cubed of permeate output. As you can see from the photograph shown on the slide, our membrane systems are installed internally in a clean, dry environment. This has a significant advantage when it comes to operating, manual handling, and environmental benefits. Our other process, which is now the aerobic process or an AMBR, adopts a very similar process stream. The only really exception here is we've now got a bioreactor that's no longer anaerobic. So we're using, the biomass is utilizing atmospheric oxygen derived from the air, blown into the reactor, and we're using that oxygen to degrade the COD down into water and carbon dioxide. Again, oh, sorry, Phil, if you pop back to the previous one for us. Again, we're using an identical membrane system. So we're recirculating that biomass through the membranes and separating treated effluent from the biomass. The only slight difference here now is that we found that the filtrability of an aerobic sludge or an aerobic biomass slightly better than an anaerobic equivalent biomass. So the number of membranes used to produce the same amount of output is less. We utilize all the same mechanisms and for backwashing and cleaning of the membranes. Okay, Phil, thanks. So the advantages of, like I say, the advantages of utilizing an ultrafiltration separation is that we produce essentially a suspended solids-free effluent. We've got a very low organic content, which makes that effluent ideal application for a downstream water reuse stage. You'll see from the photograph in the top right-hand corner that we provide membranes in multiple banks of UFs. These are provided in a series of tubular cross-flow modules per bank. And you can see just from the photograph underneath the extent that of individual membranes that are contained within each one of these modules. So typically there's about 500 membrane tubes within each module, and typically we might have up to 8 modules within a bank. So we're talking about thousands of individual membranes per bank. That allows for a lot of versatility and protection when it comes to if and when we have any potential breaches that they may well not actually significantly affect the quality of the water that's being produced. Sorry, Phil, step back one. The low energy design that we incorporate also features automatic bath flushing of the membranes to help control the fouling. We have variable speed pumps for energy optimization and flow control. And we also incorporate automated backflush cleans when the membranes do actually require a cleaning. Our final membrane technology that we incorporate is reverse osmosis. The previous technologies that we've just spoken about have produced a good, solids-free, low organic content effluent. We've now got to address the dissolved components that are left in the effluent that need to be removed in order to produce a water that is of a potable standard. So sorry, Phil. Let me step back one for me, thank you. Taking that UF permeate, we first pre-treat the effluent with acid and anti-scalant. This is to help mitigate any potential scaling that might occur in the reverse osmosis process. We then utilize low pressure brackish reverse osmosis membranes. This separates the salts within the effluent. So we produce in the light blue line a low conductivity, low salt effluent, which is ideal for recycled water and is very close to a potable water quality, if not greater than on most occasions. We also produce from this process a slightly more concentrated waste stream, or what's referred to as RO reject. That could be still of sufficient quality to be discharged to sewer, or even on some occasions, when blended with other UF permeate or other final effluent, could be discharged to a final water course. We've now got a water that's of acceptable quality for reuse within the factory. Next slide, please, Phil. This slide is just showing those two AMBR and the RO process can be seamlessly joined together in a plant, which we've done many times. So going from an effluent stream through biological process directly into an RO to produce water that is now deemed of potable water quality and acceptable for reuse within manufacturing applications. As I say, the potential uses for this reuse water. It can be blended with mains water and are used as a source of potable water within factory applications. This could include use for CIP. It could even be used in ingredient production. It could be used as drinking water or in canteens. And of course, it could be used for site or vehicle cleaning. Non-potable or effluent streams could also be used for cooling towers or washdowns. We've had applications where it's been used as a water for sorts of boiler feeds, and on the odd occasion, it also could be sold to other local businesses nearby for their application. Finally, I'd like to highlight some of the safeguards that our technologies provide in terms of quality. So the technologies that we are providing are proven best available technologies according to the European BREF documents. These offer 3 levels of protection: ultrafiltration membranes. So we're filtering down to 0.03 of a micron. This provides a barrier to solids, parasites, and bacteria. The RO membranes, obviously, then still provide a barrier to solids, bacteria, but we're now down into protecting against viruses, organics, and the partial removal of some of the salts and ions contained within the effluent. Some of them are up to 99% rejection. All of our plants which use a recycling application, we also provide a disinfection via ultraviolet light. This renders 99.99% of pathogens, bacteria, viruses, and bacteria rendered harmless, and is certified to the German DVGW standard. Finally, the water that we produce from a combination of these technologies, its quality conforms to the requirements acceptable to the private water supply regulations of all areas of the UK.
Thanks, Dave. And as I mentioned, that's a sort of contact sheet that where you can look at various case studies. It's a link to our website as well, talking about technology and product sheets, and there's videos and references and case studies in there, sort of thing. So it's can be referred to there. Thanks everyone for your time.